Well, okay, well, we are going to start the roundtable, and each speaker, member of the roundtable, will have 7 minutes, no more than 7 minutes, to say whatever he or she wants to say, and then we will be an open discussion, okay? So we are going to follow the alphabetic order, but in the opposite direction, and so I will ask Esther Ruiz to start.
Okay, thank you very much, Daniel. First of all, I want just to thank for the invitation to be here. And let me start by saying that I am not an expert on big data, so I have the feeling as some of the speakers before that I have to say something about something that I don't know. But it's even worse because I am not an expert in co-integration. So somehow I think that my role today, my hat, is going to be that of a student, a very curious student that wants to make some questions of things that somehow I don't understand or I would like to know better. Okay, so I think that today we are talking about two big revolutions in the way that we understand data and we deal with data. One is co-integration. I think, from my point of view, it helps us to understand how to deal with relationship between non-stationary variables. Before, there was some confusion. We know about these spurious regressions that were around when you try to relate time series, non-stationary time series. So with co-integration, we understood, we knew how to deal with this problem, and that's nice. On the other hand, now we are dealing with this big data where we need to deal with many, many variables, observations, through cross-sectional observations at time observations. So we can learn new things by having all this data around. So I think that one of the points when trying to see what are the relationships of how whether co-integration and big data can collaborate, I think it's important, first of all, to think about the objective, what we want to learn, what we want to do with the data. And when I talk about the objective, I mean whether we want to measure the relationship between variables, whether we want to forecast the future of variables. And in that sense, I think the objective, the particular objective, what we want to do with data is important. Co-integration works well when you have a small cross-sectional, so when you have a rather small number of time series, and the relationships are linear, and then we want to explain relationship. As David was saying before, by the way, most of my ideas have been said somewhere today, but when you just want to forecast, co-integration is not a very good idea. On the other hand, we have big data, and as far as I know, big data has a good performance in forecasting when you have either cross-sectional or stationary data. When we look at real world and we see what's happening, we observe at the same time non-stationarity. That's clear. I mean, the world is moving, so we cannot assume stationarity. So big data could have a problem in that sense. At the same time, we have non-linearity, so co-integration may have problems. And we have complex relationships. We have many, many variables. So somehow I think that the objective is important, what you want to do with the data, what you want to learn from the data, and depending on the particular environment, the particular objective that you have, you may need one kind of procedures, co-integration, you may need big data, or you may need to combine. And by combining, I think that the way that David Henry deals with data is really one way of thinking about how to go ahead. We need to deal at the same time with non-linearities and non-stationarities, and this is somehow that what I think is going to be the future, or at least one way to go to the future. Okay, and let me just finish by mentioning that with respect to one of the questions that Jesus was putting forward about how co-integration starts and what's happened with the paper. And you can correct me, but I was reading a paper by Clive Granger in 2010, and according to him, they start talking about co-integration in the early, David and Clive were talking about co-integration in the early 80s. They were discussing about the balance of error correction models, and I am quoting exactly Clive Granger, so don't just complain about that. They were mentioning error correction models. And Clive, from these discussions, wrote a first paper that were rejected by Econometrica for various reasons. And according to Clive, because they wanted a deeper theory and some discussion of the testing questions and an application. So at that time, Rob Engel came about, and he just collaborated in the testing part, and in the application, they sent the paper again to Econometrica, and it was rejected again. And the reason was it is not sufficiently original. So the paper was rejected twice before finally people, the editor from Econometrica, called them back asking for the paper, and finally, obviously, we know that they published it. Okay, so that's all for me. Thank you very much.
Okay, thank you very much, Esther. And now, David.
Following up on that story, Dennis Sargent was the originator of the idea in his real wage model of 1964, where he showed that you shouldn't be modeling these variables in levels. You should be explaining the rates of inflation of wages and prices by the feedback of real wages relative to productivity. That's the kind of share of labor. As it fell, they wanted higher wages, and that led to higher prices, and off it went. In the early 70s, 1975, I fell out very badly with Clive because he gave this paper in what I called nonsense about nonsense regressions. He was unaware of Yule's work and was unaware of Sargent's work. Yule's work did everything they did and a lot more besides, and Sargent showed that theirs was a non-problem, roughly along the lines that if you stick in a lag, I think Juan raised this, if y and x are two bits of rubbish, but you put in lagged y, the rubbish bit of x goes away. And Clive got very angry about the suggestion that what they were doing was a load of nonsense because he felt that it would permeated literature and denied that you could find the levels of variables being connected when they were non-stationary. I said, of course you can. Absolutely obvious. And it was so obvious I never bothered looking again at the problem, which is possibly a mistake on my part, since he got a Nobel Prize for looking again at the problem. But he only looked at the problem in order to prove you couldn't do it, and then discovered you could do it. So we had called the processes error correction in the 70s because we didn't think of regime shifts. And within regimes, equilibrium correction does error correct. It's one and the same thing, because if you're out of equilibrium, it moves you back towards the equilibrium, and we called that error correction. So we hadn't thought about the change between regimes. But by the 80s, Clive's first paper was really 81, and I think he also had a comment in a paper by Jean-François Richard and myself on co-integration that we began to take seriously. Graham Meisen and I nearly discovered it in a simulation that we were doing in 1976, criticising the Bank of England, which differenced everything and therefore lost all the long-run information. And we showed you could keep the long-run information, but we didn't realize the importance of the intercept in non-stationary processes. And so, in fact, our trends were going off to infinity at a very rapid rate, and we showed it made no difference what you did. You got the correct answer all the time. If we hadn't put in intercepts, we'd have seen a big difference. Anyway, the paper with Rob and Clive was rejected by Econometrica until I told them we would publish it in that special issue of the Oxford Bulletin in 1986. And Rob went to Econometrica and said, look, you're going to lose this paper. It's going to go in the Oxford Bulletin special issue. And they immediately accepted it. I have never had so much power in my life on the world. Unfortunately, we didn't get it in Oxbull. That would have been the Oxford Bulletin special issue. It would have every paper of any interest ever in co-integration in the one special issue in '86. But we got most of them. And another one from Clive, who, like me, felt that Econometrica was a magazine of archive and not really a publishing area that you'd want to be bothered with. So that answers that. I don't know what happened to the paper with Andy Wise. He did exist. It wasn't kind of the twin studies in which the research assistants were invented by the producer in order to make the twin studies look real. No, he really did exist. I think a version of it was published, but I couldn't say where it was. It's in a book. That's where it is. That's right. It appeared in a book. Thanks, Alvaro. And so the literature got going. The big data side, well, yes, I think most of what people have said I very much agree with. The nonlinearity I didn't discuss today because once you've got 20 variables and 50 lags, you have to ask at what time period does the nonlinearity kick in? Is it contemporaneous, lagged 1 or lagged 10? Right? And you can't possibly know that. So although I was joking about having 1,000 variables and therefore 3,000 nonlinearities, I do think you need that. And our method is just a very crude approximation, although we did show that if you've got the squares, they deal with power 4, and if you've got the cubes, they deal with power 5. So actually, you've got a very good approximation to power 5, as well as the exponential, by putting in our polynomials in the individual components from the principal components. But it's still very big. And then you have to sort through them to find out what matters. And the thing about all the data being highly correlated is that when you square and you get all the z's, you have to cancel many of them with other components. So it can take you quite a long time to see which of the z's are actually doing the work, which is what you'd really like to know. You're not really interested in the principal components coming in. But I think that can be done. We're looking at even bigger problems at the moment because step indicator saturation and impulse indicator saturation both have the same number, approximately, of indicators as observations. So if you've got 5,000, you've got 5,000 of each, approximately. But we're looking at what's called multiplicative indicator saturation, which you multiply every variable at every lag by every step indicator. You get quite big quite rapidly. But that lets you pick up shifts in the parameters over time, as well as shifts in the location and shifts in outliers. And it will become quite an important tool. It's been languishing for a long time. Because my doctoral student hasn't followed it up, and Søren's colleague who was working with my doctoral student hasn't followed it up. So we're now beginning to get back to that. It does work. It's really surprising that it works, but I've always been surprised in this game how little cost there is to doing massive numbers of searches if you do them properly. And with multiple indicator saturation, you've got a variable, it's multiplied by an indicator. You'd be really surprised if I told you the parameter was 0.5 up to 1990 and 0.9 there onwards, if when you fitted separately to the two samples, you didn't find that. And that's all that you're doing by searching. It throws out the ones that don't matter and it picks up the ones that do. And it really does come through very well. I haven't tried it in big data, but we're doing it in quite a number of climate-related variables where you get odd results in climate if you don't allow for parameter change over time.
Okay, thank you very much. Søren?
I'm a little lost. I'm very tired, and I can't think of anything intelligent to say now, except one thing, which is one of the serious issues about co-integration is it's too difficult. We have tried to teach in the summer schools, and 3 weeks of hard supervision by Katarina will produce a reasonable analysis. But that doesn't happen in any university anywhere. And that means that I receive a lot of emails from people saying, what does this output mean? You know, they've run eViews and you get all sorts of things. Of course, I have no idea. I don't know eViews. It's pretty obvious that people want to use this method without spending any time whatsoever on reading it or trying to find out what the concepts are. So I think if it dies, it's because people don't want to learn it. I don't know if you can use that for an contribution.
Okay, Tony?
Okay. Well, as many of the speakers this morning, I am not an expert on big data. The only thing that I have approached has been working with hourly and daily electricity data for several years, and also daily data for petrol prices, but not a proper job on big data. About the main topic of today, co-integration and big data, my view of the things is the big data corresponds to low and very low frequencies, and therefore they are dominated by short-run factors. And in that context, the deviation from possible equilibrium paths do not matter much, and certainly not for forecasting purposes. So from my point of view, co-integration is not a main issue in big data. Nevertheless, if co-integration exists in big data, you should test it, but I could say that not as in the original way, the data appears, but after some aggregation a long time. And here the results by Clive and Massimiliano Marcellino are very useful. As we saw in the transparency of Alvaro this morning, the trend does not disappear aggregating a long time. So if that not disappear, we could test co-integration aggregating a long time and not testing co-integration at hourly or daily data, but testing co-integration at monthly level, and then following the results by Marcellino, impose those results in the low frequency data. Well, before I finish, I would like to give another interpretation of co-integration, but first let me talk about peculiarities of big data. Big data, we are talking about 10 of million observations, or in the project by Professor Roberto Rigobon, billion price projects. So before we could apply time series analysis to big data, several questions must be dealt. First, data depuration. Because of how the data is collected, there are plenty of errors in the data collection, and the example by Galeano and Daniel Peña is very illustrative. They started with 15 million transactions on purchases in a big supermarket, and after depuration they are just left with 8.3. So depuration is necessary. The other question is when we are going to apply time series analysis to big data, we need to aggregate over time, to aggregate over agents, or to aggregate over both. Sometimes the original data is already aggregated. For instance, if you work with 5-minute electricity consumption, you have 1.5 million data points, but they are already aggregated over units. Aggregating over agents, this work by Conde et al. Is a very good example. and they have microdata for new contracts in the Spanish economy, and they aggregate in order about the units in order to have a daily time series, and there they make a beautiful job in studying the effects of the calendar for recommendations of policy. Also, in this work by Cavallo and Ricopodon, they aggregate over agents and over time, and from these billion prices, they end up with GDP, CPI indices for many components for a lot of countries. Well, the other question is about the classification. Data must be classified very often before we could apply. And this example by Bodas et al. At the Banco de Bilbao Vizcaya Argentaria in Spain, they use transactions with credit cards, and they need, after some aggregate, to classify the data. And in that case, they used the official classification of the merchants. In another occasions, the authors must design the classification, and Galeano and Peña is an excellent example on that direction. But more often, usually what people do is they apply agglomerative hierarchical clustering that, well, I'm not an expert at all on that, but I always suspect that there is some sort of black box over there. Another point I would like to make is to distinguish, when you work with big data, you have a lot of proper outliers, so the discordant observations that have been caused by unknown factors that you cannot discover. And they should be corrected for that. Possibly the outliers correction should be done jointly with the selection process as is advocated in the paper by Dornick and Henry. But after outliers correction, still you, or jointly with that, you have the problem of what I have denoted outstanding observations. Outstanding observations are apparently discordant observations, but they are not outliers because they can be explained by causal factors, usually meteorological factors and calendar factors. And in many fields of big data, you are going to find outstanding observations in consumption, in daily data of labor markets, in payments, in bank transactions, pollution data, sales, traffic, cities, occupations by means of transport. In all these cases, you are going to find outstanding observations, and you must deal how to model them. I'm running out of time, so in order to do that, you need to design complex dummy variables for the calendar effect, different regimes for meteorological variables, and the interaction of both. And well, you have here some examples where I have applied that. But nowadays there is one way to do it perfectly. If you are worried about calendar effects, you design all possible complications of the calendar effect connecting with different cycles, and you define all those variables, and then allow Autometrics to select the final model for you. Well, and the same it could be said for the meteorological variables. Right, let me. Well, from big data, you can construct leading macroeconomic indicators. That is a very promising procedure. But the cleaning from calendar effects and meteorological effects should be done. And so, and to end, I would like to comment about another interpretation of co-integration. If you look at a series of production, of series of prices, and you look at very disaggregated level, 100 or 200 components, you find that some share some common trends, and it's not
Tony, 1 minute, please.
Immediately, and it's not because there is a theory behind that, but it's just a regularity in the data. But this regularity in the data can be discovered giving a restricted version of co-integration as this definition of fully co-integrated subsets, then you could find these co-integration relationships, and they will help you to forecast. And you could find this useful in these sectors. Thank you very much.
Thank you, Tony. Well, I would like to ask a general question to the people in the table and also to everyone that wants to give his or her opinion on the subject. And I would like to bring a little bit the point of view of people working on machine learning, and that they have developed, as you see, many useful procedures that are producing interesting results and also making cars that drive by themselves, and many other applications in which statisticians and econometricians have not had really a big impact. Their point is as follows. Statistics and econometrics is very good for aggregated data. There is no doubt about it. If you aggregate, you have linearity. For aggregate data, you can build theories, and you understand the relation between variables, and so far, so good. But suppose that you want to try to understand images and the relation between the pixels and classify images. Or there is a car, you want to build a method for a car to drive by itself, and then you have to understand how people react very fast when you see immediately something in the screen that goes fast. We don't have no idea at all how our brain works and what are the things that everybody sees. And people react in different ways. So, as it is impossible, we understand exactly how our mind works, and there are many experiments on this, and also people behave in very different ways, so we have to understand how the driver is able to behave in a particular situation, and then devise method that works in this practical situation. And so, statisticians have not made much, or econometrics, much contribution to image analysis, that's clear. Most of the procedure of classification or speech recognition, or many other problems in which you have very disaggregated data, very nonlinear data, and then the usual, let's say, linear and statistical procedures that have proved to be very useful in science. There is no discussion about it, and very useful for aggregated data, are not going to be useful if we try to understand how not people behave in general, but how each consumer behaves. And now we have the possibility to do so. For instance, in one of the papers that Tony referred to, we were looking at millions of people and the data given by a bank, and we have how people behave, 10 million of people, how they behave every day, and how they spend the money, and how kind of transactions they have. So we have a lot of information, not complete, but more and more we will have having more and more information about the behavior of everyone. So do we have procedures and ideas on how to understand each individual behavior and then to put together all the information to really understand how the economy behaves? Because maybe, as everybody knows, when we have very aggregated data, we may get sometimes the wrong impression just because some part compensates with another one and there are linear behavior that we don't see. And now we have the possibility that it has been discovered in many areas that is very useful. For instance, in genetic, for instance, as you see, the treatment of cancer is changing completely because it's clear that not everybody answers in the same way. And instead of thinking of a treatment in the average, people are trying to work in a treatment for each person. Of course, we are very far away from this, but that's the objective, and we are trying slowly going in this direction. And so in the same way, instead maybe of talking of the behavior of the average company, we have to think about the probabilities of success of a particular company and learning from experience. And the question is, do we have the right tools to do so? Are we moving in this direction to learn or not? And so anyone that want to answer?
I think we have some of these tools. I mean, if you think of functional analysis in some sort of way, dealing with images should not be too different from that. Second, we have a clear case for evidence coming from experimental devices. So if we have the self-driving car, and all of them, we make an experiment where someone all of a sudden crosses the street or a zebra path or whatever, we can examine different individuals with different characteristics and how the car responds to that. So, and for that we have all the tools. So I really do not feel that we are short of that sort of tools. That's my opinion. Mm-hmm. I mean, of course, we are far from the perfect information, but I mean, if you look at what has happened in genetics, I think we can achieve exactly the same. It's treatment. I mean, we have all these treatments. We know that it must be heterogeneous by individual. The same treatment applied to you and me may give different results because some are unobservable that we have. We are conditioning on observables, but the unobservables are different. Well, the same can happen with the type of outcomes and treatments that you are thinking of. So the fact that there are these images and so on, I don't think it's such a big challenge.
Okay. More comment or question in general over any subject related to the roundtable? Yes, Álvaro?
One question.
Mm-hmm.
Okay, by doing simulation, for example, you can simulate an AR1 process with changing variance. If you forget that the variance is changing, you might detect that this is an AR1 process with outliers or level shifts or whatever. So if that can happen at the individual level, imagine this at a highly multivariate level. So should we treat this as always departure from linearity, or should we allow the variance to change and model simultaneously the mean or the variance? Because the model will end up totally different. So the question is, with big data, how should we do that? I mean, even with small data, it's not that clear, but with big data, is there any clear approach if we should look for more constant mean or more constant variance, or modeling simultaneously and find automatic procedures that simultaneously model mean variance, non-linearity mean variance simultaneously? I don't know. That's the question.
Okay, as I said, I am not an expert in big data, so I don't know which kind of instruments they are using, but somehow I think what you are asking about modeling mean and variances, it was a way of simplifying the models when we don't have a lot of data. I mean, before we try, I mean, the idea was to have the full density of variables and relationship. If we can have the joint distribution of several variables, we can just answer anything about probabilities. Obviously, we need to simplify, and we were just thinking about mean, then we just incorporate the variance. But somehow I think it was like simplifying the problems to understand them better when we have not a lot of data. Now that we have a lot of data, I think these kind of black boxes, somehow they can help to model, although maybe they don't have an interpretation. So I think it's like a price to pay. And with respect to what Daniel was putting forward about the car, I think if the world is stationary, then we can just move with this kind of data and the models. That my problem, or what I don't understand, and I insist, I mean, I don't know enough about the tools that big data are using. But what's happened when it's non-stationary? I mean, think that you try to program the car when you have an earthquake and things are moving all the time. I mean, it's impossible. So somehow that's why I think it depends on the objectives, it depends on what we want to do, what we want the data for, what we want to extract from the data. We can use different instruments, and using what we know from, say, the most standard world when we need to simplify and we need the models, and we have this data generating process that we know that it does not exist. I mean, it was just to simplify our lives. To know from here and to know also from this kind of black boxes. When we need to combine these two things. That's my point of view, I mean, but it depends on the problem. Because if things are stable, maybe just big data kind of instruments are okay, and that's it. But when you have the earthquake, that's more difficult.
I'm very sympathetic with the problem of forecasting the individual behavior. And having millions of observations of individuals, for me, a crucial thing would be to organize a huge classification in which, in each group, the individuals have some homogeneity in their behavior. And you could use, having millions of observations, you could use 1,000 different groups in classification. And then the aggregate of the classification, you have an initial pattern of behavior, and in that way, it will be, in the next step, it will be better to forecast individual behaviors. But possibly this intermediate way of model the classifications, it could be useful.
You are speaking from clear perspective of econometrics, and you are speaking about co-integration. But the issue is that there are two different approaches that can be complementary. And I don't agree with, I agree more with Daniel about there are questions that there are not econometric tools to deal with. For instance, you cannot recognize, face recognition is not, and these sort of things, of course, are not possible. And also I want to say that machine learning is not always black box. You can learn, and you can, for instance, to study causal relation, there are some useful tools as the Bayesian networks that, of course, don't produce exact causal relation, but can be used to study such influential conditional probabilities or influences that can be very useful to study this sort of things. So I think the two ways of thinking, the two approaches can be complementary, and you don't need to decide on, it must be work together. For me, it's clear.
More comments? A
Could I-
question?
Sorry. No, fine.
Okay,
No,
go ahead,
some-
please.
Hello. First, congratulations on the workshop. I would like to elaborate maybe a little more from what Pilar says. I am a mathematician, and I came to the world of econometrics like 10 years ago, and the first thing I really, I was amazed was that in the economic world, people were using like what for me is very old mathematics and trying. There is nothing like topology in there. When I learn about cointegration, cointegration is just a straightforward application of mutual information, Shannon, 1940. And it's very straightforward. It's trying to see what the information that two variables share. And then we are using a lot of machine learning when I work at ethics. And I agree with Pilar and says that machine learning, it uses a lot of tools in data analysis that can reveal what reality is like, not all of it. And then some of the facts that you see there, some of the relationships, people who work with big data, they always say that they have uncovered relationships. They never speak about cause and effect. They never speak about nothing. It's just there seems to be a relationship in there. And then there are like theories or to try to understand the relationship. And in some cases, econometrics and cointegration is helpful to model this relationship when all the assumptions apply for doing that. So I agree with her in the field that I think that cointegration is very useful in econometric studies, and it can use big data analysis and other kinds of data analysis just to explore more relationships between or those variables that are supposed to reflect our reality.
Yes, it was a sort of comment back to Alvaro that clearly in finance they get round the problem of changing variances by looking at realized volatilities over very high frequency periods and then look at it changing over time, so you can take account of it that way. On the other hand, they're still making an assumption basically of stationarity. And when you look at the kind of results that come out of modeling realized volatilities, they've often got a unit root. And that unit root probably corresponds to the underlying unconditional variances changing but not being modeled by the people who are doing it. But you could certainly tell the difference between outliers and changing variances if you had enough intersample observations to do so. But clearly, if you're, as I am often at annual data, you're never going to be able to do that. There just isn't the information. But if someone suddenly gives you monthly data, well, you've got 12 within period things to look at the variances, and then you can start looking at them kind of overlapping periods to see how it evolves. And then if they are over and above having taken account of outliers, because you only pick up of an outlier if nothing else is explaining it. So if your variance is a realized volatility in the model and is explaining the change, then the outlier will not pick anything up. So that you can actually tell the difference between them. And similarly with nonlinearity, that you might get a nonlinearity, it comes along and looks like this. But if it's modeled, then you could still put in a set of indicators for it and they won't pick anything up. So there are ways of telling the difference between these, but that's not really a big data issue.
Okay. Well, regarding these issues about outliers, I had a comment, which is, I mean, there seems to be this segmented approach. I treat outliers first, and then I treat the rest of the model, and then I interact them with the impulse indicator saturation procedure. If you think about how we take actions, so first, we do it in 2 stages. First, we decide whether to take the action. And later, if we decide to do so, we make a decision on the intensity. So first, I decide whether I want to work. And second, I decide if I want to work, whether I want to search for a part-time or a full-time job. So some of these outliers may be crucial to explain the decision problem, the first stage of the decision problem, the so-called external margin rather than the internal margin. Let me give an example. Suppose you want to analyze female labor force participation in the US and most European countries. When did female labor force participation increase a lot? Well, during the world wars, especially in the Second World War. Why? Because men had to go to war, to fight in the war, and women took those jobs. And then all of a sudden, society realized that they were as good or even better than men. So if you take that period, in one of your slides, I remember, though, take outliers like wars, etc., aside, you are losing the main message of the paper.
Shocking.
Yep. And
can I just add that in most of our studies, we don't find the war periods being exceptional, right? If you've got the right data, they
it's
describe
just an
what's
example
going
of
on.
that.
Yes,
Many
sure,
of-
no, I agree that. Whereas things like government interventions in a food program during the Great Depression has an enormous impact on the demand for food, and there's nothing you can do about that except treat them as outliers.
Any other comment?
And a second comment on machine learning. I think machine learning is welcome, it's wonderful, but it could be dangerous in the wrong hands. I mean, I think there is this divorce, especially between econometricians and economists, which are working in different ways. I think this issue about black box, maybe the others are putting too much theory, but I think machine learning in the hands of the wrong people could become, in the words of this book by Cathy O'Neill, a weapon of mass destruction, rather.
Well, very briefly, I agree with this, but maybe in some areas we are in the situation that I think that Professor Johansen have described with the example of Gauss and Fisher, that you think, well, what's sensible in this situation? You should give the mean, and then you build the theory. But first you have some experience, because we have to understand that, having astronomical observation in Gauss time was a new thing. We have not experience about this, and then something to think, well, or very few. Especially taking for a clear objective, as was testing Newton's theory at that time. But so, in fields in which we have no experience, and this is image analysis, I think is much more complicated than functional analysis. By the way, much more complicated by the studies. I did some work long ago, and then I have followed a little bit the literature outside the statistics, and really they are doing some things that are, that the statistician cannot imagine. So they are very far away, but in my opinion. But again, the question is that sometimes we don't know about an area. You start taking data, so try to understand what's going on, and then maybe theory will come first. Maybe at some point of time, we have a clear idea of how the pixels are related and how they change over time in an image, but clearly it's not an experience that we have every day. And even, we don't have even no feeling and no theory about what would be the relation between different images and so on, apart from some very vague concept of spatial statistics, that there should be some kind of autocorrelation and so on, but it's a nonlinear effect, so autocorrelation is not very useful. But anyway, the second example of Fisher, I think that that Professor Johansen showed up, again, is very nice, because, there is an intuition, and then theory many times have come later. And so maybe in some areas, people in machine learning in opening this black box, and if there is some regularity, and I agree with you completely that it could be very dangerous, but if there is a clear experience one after the other, and well, it seems that there are cars driving itself in the street. Of course, it's not perfect, but it is amazing, for me at least, what they are doing. And then, so when we have more and more experience, then maybe we can be able to build theories, and that I think that is the objective of science at the end. But that we can, I mean, all the result and the effort that many people are putting in this area could be very useful. I don't know. I have no idea. So I was not trying to argue for a point of view, but I think it's one thing that we should look at carefully, and I think that they are developing interesting theories as well and useful results. That was my point. Well, any other comment? Well, I think that we are running out of time, so let me thank the members of the panel for their contribution and all the speakers for this interesting workshop. Thank you very much for you for being